Hey folks, this is my ongoing exploration of spatio-temporal moments. I've decided to expose some of my early thinking in it in a more graphical manner rather than doing it as a purely verbal discussion. Previous two videos I did have a couple of graphs up. I'll be repeating those. I'm going to do a brief explanation of each graph. I just want to capture it down on the video channel so folks can watch how what I consider personally to be scientific characterization of natural phenomena can move forward, beginning with a concept. And the concept was there's kind of like a matrix of points throughout all of space, which when the Big Bang occurred turned it into space-time by causing oscillations in these ultimate particles. After doing my original spade work, I discovered the Higgs boson, which has been discovered by CERN, a particle accelerator smasher in Switzerland. The mathematics behind that assumes a non-zero spatial field, so you can think of spatio-temporal moments as the essence of that non-zero spatial field going out through all aspects of the cosmos. And you can think of the Big Bang as an event that caused such a serious amount of stress in that field that it resulted in the particulation of matter. Inherent to spatio-temporal moments are such things as gravity, because they are neighbors to one another and they are to some degree or another attractive of one another, and electromagnetism. Inherent also in spatial-temporal moments is the what I consider the strong probability that if spatio-temporal moments are exposed to too much energy, they become entangled with one another because their purpose is to dissipate energy. And if there's too much, they get all stressed out, they entangle, and they create particles, most of which are short-lived, have very short half-lives, some of which can be almost sustainable, although I do believe that all spatio-temporal moments will eventually once again reform after whatever stimuli was released by the Big Bang has dissipated sufficiently. And one way of understanding that is to look at the cosmic microwave background radiation, which is about, well, maybe a couple degrees above absolute zero as a electromagnetic phenomena in space and in time. Let's move on to the next exploration. Here we have an image you've already seen. I have blackened it in a little bit to make the contrast better. I've also left certain kinds of information in pencil because I may make changes in the future. But basically this is what happens to a spatio-temporal moment when a neighboring spatio-temporal moment, which it is bound to both gravitationally and electromagnetically, is stressed by the passage of energy, which we perceive as a photon. Now the photon is an epiphenomenal of this stress, but essentially a photon is a package carrying energy over space through time, although it itself doesn't really experience time. It just this is just the transmission of energy through spatio-temporal moments when they act in their normal mode, which is simply as a medium of the transition of light or translation of energy from one part of the cosmos to another in order to dissipate all that stress as quickly as possible. You notice we have a waveform. The waveform is essentially round. The frequency of oscillation has to do with primarily the amount of energy that has been absorbed by a spatio-temporal moment. The excursions can probably vary, but the excursions in the waveform probably relate to the influence of neighboring spatio-temporal moments, which also are attempting to dissipate the energy, unless, of course, you're using the laser light, which has done something to the spatio-temporal moments through the use of crystallization to focus that beam of stress along a single line, even though lasers do dissipate and take on girth as they propagate through space. Natural form of spatio-temporal leakage to their neighbors. Here we have what would be from a behind view of a spatio-temporal moment in 2 dimensions. Remember, it's a 3-dimensional phenomena, but we're looking from the back. So here we have the point at which a neighboring nuclei of a spatio-temporal moment has begun to oscillate and then transmits part of its oscillation to the frontier of the nuclei of spatio-temporal moment that we were thinking of. Think of the nuclei of a spatio-temporal moment as being about halfway through its diameter. It's a sphere in all directions. I just give it a radius, a diameter of 1 and a radius of 0.5 for just some mathematical explorational purposes. So this is the receptive pole. It's closest to a previously activated STM. Starts at 0 degrees, a theta of 0 degrees. It unwinds. It goes all the way out to its furthest extent, which is right there. And then it begins to collapse as it dissipates its energy into its neighbor or neighbors. And here we have now this collapse of the waveform spiraling in until finally the stimuli in the form of energy exits the spatio-temporal moment, being passed along to another. Now you should keep in mind that these waveforms can be incredibly long in terms of photons. I mean, we have wavelengths that go on for meters after meters, as well as microwave, light, and beyond. So basically you can have a whole series of spatio-temporal moments, all building slowly across the entire train of them. There could be billions of STMoments involved in the transmission of a single oscillation. They're very tiny, presumably, and this is at the very end of each of the transmission of all that energy. So you can imagine that this previous image here where you see an oscillation here is not dissipated. It just hits at its extreme, and all it does is, like a spring, transferring all that energy to its neighbors in a spiral-esque fashion. One initial exploration of spatio-temporal moments was a tangential distribution. In other words, you have individual discrete nuclei of a moment, and there is a boundary, and that leads into the realm of the next moment at the very peripheral of the boundary. I didn't find this very satisfying. I tend to think of them more being along the lines of this, which means the moments have a nuclei and its sphere of influence extends all the way out to the nuclei of the next moment. And this extension occurs most immediately in front of the moment, behind it, to its left, its right, and above and below, which means it has 6 immediate neighboring interpenetrative spatio-temporal moments. And the beauty of this approach is its area is, in terms of its diameter of any given region of moments, more and more begins to approximate a perfect circle as you expand out from the ST within the ST momentary field. So I've landed pretty much, at least initially, on the interpenetrative approach. So each of these moments has a radius of 0.5, a diameter of 1, just as a unit, hypothetical unit, that interpenetrates to the radius, the nuclei of immediately neighboring moments. Okay, here we get an idea of how light propagates and energy propagates. A moment receives energy in the form of stress, which we would call a photon, or actually a part of a photon, and that energy begins to dissipate out away from the direction of other moments that have already been stressed by the transition of that photon. So now you get this dissipative effect, which is wonderful for STMoments because they don't like stress. They want to oscillate back down to a normal, almost null state, where all they have left is the potential for electromagnetic interaction with neighboring moments as well as a gravitational pull. each drawing all of them together into the spatial matrix. Now I do want to point out that the spatial matrix of STMoments isn't precisely perfectly matricized. There can be a lot of jostling and fluidity going on, and so we're only using a static approach like this to kind of get a sense of what it might look like. But you can see how all these interpenetrative STMoments are interacting with each other. Now in terms of a laser, we can assume that somehow you've managed to polarize the light in such a way using crystallization that the propagation now is linear rather than dissipative, which means the energy level at the beginning of the laser is almost exactly the same energy level at the end of the beam of laser light when it makes contact with some material substance along its path. Now actually there's going to be a minor amount of dissipation. So really lasers basically approximate to this kind of a linear dissipation, but there's going to be some lateral dispersion of the energy from the laser as it goes along. Now one thing I want to point out is when I came up with the idea of spatio-temporal moments, I didn't know that the Higgs boson is assumed mathematically to be in a non-zero field everywhere. That's a Higgs boson on Wikipedia, which basically says, okay, I had an a priori concept that this thing was everywhere even before the Big Bang, and then I read in Wikipedia that the Higgs boson, which may very well be the grandfather of all particles that are sustainable and those that are unsustainable, actually assumes there is a non-zero value for all of space, which bumps up the probability that this concept of spatio-temporal momentary energy dissipation, it's pre-existing the Big Bang, is actually close to hitting the mark. This next little sheet here, which I've done several of these now I've done since my original exploration of this concept of moments, basically shows you that there's an envelope of moments around a central moment. There are 6 that basically project left, right, above and below, front and back, and then they have neighbors they're in contact with. We can call them secondary. I now have new language. It's now called intermediate. So these are immediate moments around the central one. These are intermediate, and then there are remote or distant moments. All of these, as we will see later, have line of sight from any single moment. So if you're at the nucleus of any moment in your imagination, you look out, you're going to actually see 22 other momentary nuclei, or experience them in space around you, some closer, some more remote, and my speculation is they can all participate in the transmission of energy based on their remoteness, and they can all participate in a collapse into some kind of entangled particle should the energy level get so high that the moments can no longer handle it. That is what we call stressor theory. Moving on, I did put together a kind of a matrix of the field in order to explore it. Now once again, this matrix of spatio-temporal moments is not as nearly as regularly laid out as this. I suspect this kind of a very regular layout, like a matrix of cubes with circles, or circles that are all together and cubically related in space, probably is what ultimately happens when entropy in the universe finally decays everything to a point and all the subatomic particles have disentangled and all the moments have once again been released as moments, and after a long period of oscillations they finally stabilize themselves out. So this is probably the initial and end state of a moment. Now in a previous video I pointed out that the Hindu philosophy basically says there's periods of Mahavantara, and Mahapralaya, which means Mahavantara is when the Big Bang lightning bolt strikes from beyond, which I would call a transcendental, which I think is essential to understand the nature of the universe, that there is a transcendental reality, until the point where all that energy finally is withdrawn and dissipates and everything chills and everything goes back to its normative state, which is approximated right now by the cosmic microwave background radiation, which I would suggest to fellow astronomers, amateur or professional, that they start to examine that phenomena from the point of view of spatio-temporal moments, forming a matrix. My last work for this video is what I call a spatio-temporal momentary map. And this is how I arrived at the 22 visible nuclei from any given nuclei when the spatio-temporal momentary matrix is cubically laid out in space. So any spatio-temporal moment, which we'll mark here, has one above it and below it, to the left and to the right, to the front and to the back. Each of these may have other moments that are related in the same way, but they are not blocked by other momentary nuclei, which means there's going to be some kind of subtle influence, remotely expressed. And if you examine this chart, which is really complicated because I had to work it all out in my imagination, you'll basically find that I articulate that there's a central nuclei of a moment. There are 6 intermediates that it can be seen that are closest, and those are within 1 unit of distance from it. So each nuclei has a sphere of 0.5 in terms of its radius. Within the region of those 6 intermediates are 8 intermediates that are further away but are still visible as nuclei, not being blocked by other nuclei in a stabilized matrix. And each of these has 8 distant moments, and those distant moments basically can be seen without being blocked by what we might call the nuclei of another one. And what I mean by seen is there's bound to be some kind of influence between them. And the volume of a central nuclei is roughly 0.524. Using the formula, the volume of a sphere is 4.3 times pi r cubed. R is assumed to be a half, or a diameter of 1, and I use 22/7 for my approximation of pi. I like the number. It's maybe a little high by about 1,000th or a couple thousandths for pi, but it's easy to put into a calculator if you don't have a pi function, and I haven't been able to find one on my laptop. You go out to the immediates and you have a sphere whose volume is roughly 4.190. Now it's going to be less than that. I treated it as a sphere mathematically, so the value is more likely to be maybe around 3.5, or who knows. I'll have to explore that later. If you go out to the intermediates, now you have a radius of about 1.5 and the volume is 14. Now notice as you get further and further away from the central nucleus, the more and more and more you're going to fill the gaps in terms of creating a perfect sphere. So ultimately, at a certain point, the volume of any spatio-temporal moment sphere expanded out into the distance infinitely is going to become a perfect sphere. Now whether that is true, I would suspect. So we can say that the matrix of space that existed in perfect harmony with spatio-temporal moments before the Big Bang was a perfect sphere, because all the moments would have arranged themselves in such a way that they could gather together using their basic electromagnetic and gravitational influence, which is imparted to them from who knows where, what knows where, and there's no accounting for it, but these behaviors are seen in nature, that they would ultimately create a perfect harmonious sphere in which all stress is relieved, and then, bang, you might start all over again. So, however, that is the fundamental we begin with spatio-temporal momentary moments to understand the larger theory of the cosmos, which I call the stressor thesis, which, if examined from the point of view of its basic characteristics, I may arrive at a stressor theory, but it will require others to do the deeper mathematics and devise the tests necessary to develop that thesis into a theory. But ultimately, if it should succeed at proving itself out and being related to every aspect of reality, it would become what I call a hylozoistic law of the cosmos, explaining everything, everywhere, except for its own origins and wherever that Big Bang lightning strike may have come from. So signing off, I think we're about 4 days before the total eclipse, which sweeps up from Mazatlan in Mexico, through Mexico, into Texas, slightly through Oklahoma, Missouri, goes all the way up to Maine. Happy, happy, joy, joy to all those who may be able to see the moon's shadow in part or in full along its path, and hopefully we will have the weather necessary to do so. I could say carpe noctem, but this is by daytime, and since this is part of the astronomy thread, I'm just going to say carpe diem et noctem. Adios.